Chemistry for AAQ, Unit 2 Chemistry. This video is about the reactions of sodium, magnesium and aluminium. So, period 3 metals, sodium, magnesium and aluminium. We're going to look at the reactions with oxygen, with water and with chlorine. I'm going to talk about the properties of the element, look at the equation for the reaction and some properties of the products as well, and one or two trends as well. Quite a lot of information in this video. So we'll start with sodium. Most of this you know from GCSE anyway. Sodium is a soft silvery metal that tarnishes in air. Okay, so a very soft metal. You can cut it with a knife. It looks dull on the outside because they say it tarnishes, it reacts with oxygen in the air. But when you cut it, it's actually shiny on the inside. So we keep sodium in oil. Sodium metal is stored in oil to stop it reacting with the air. When it does react with oxygen in a flame, it burns with a bright yellow flame. Yes, yellow is sodium. Remember, yellow, sodium. And the equation there, sodium plus oxygen goes to sodium oxide. And you look at this equation and you should see that it's nicely balanced, a lovely balanced equation there. Sodium oxide is a white powder involved in the production of glass, apparently. Sodium reacts violently and exothermically with water. I'm sure you've seen it demonstrated in a chemistry lesson, group 1 metals, and you wipe off cut a little bit, wipe off the oil, put it on water in a trough, and it whizzes around, floats around, hissing around, and sometimes it catches fire and explodes, giving off lots of heat. Okay. Now the reaction sodium plus water goes to sodium hydroxide plus hydrogen. There's the equation all nice and balanced, and the solution of sodium hydroxide is a strong alkali. Yes, after you've seen the fizzing and the explosion, you put some universal indicator in there and it goes purple. Do you remember that? Sodium hydroxide, commonly used in cleaning products, for example, drain cleaner, and it's also used in paper production as well. So sodium and water goes to sodium hydroxide plus hydrogen. Sodium reacts vigorously with chlorine to form sodium chloride. So you heat up your piece of sodium and you put it in the jar with chlorine gas, and there's a bright reaction, and we get table salt, sodium chloride, what you put on your chips. A good example of two very reactive elements, sodium and chlorine, and you get something very, very stable, sodium chloride. Magnesium. I'm sure you've seen magnesium ribbon. Yes, magnesium, a shiny grey metal. It's got a low melting point and a low density. And when you set fire to it, I'm sure you've seen magnesium ribbon. It is very, very bright, a brilliant white flame. So magnesium plus oxygen goes to magnesium oxide. You should check for yourself that these equations are balanced, by the way. Magnesium oxide, again, it's a white powder. Various dietary and medical uses, for example, as an antacid. So if you've got a bit of stomach acid, take some of this to neutralize it. And a laxative, if you're a bit constipated. Now, magnesium reacts slowly with cold water, and this is because you've got a layer of magnesium oxide on the surface. It does react vigorously with steam, and it appears to burn. So in this photo here, you've got some cotton there soaked in water. And when you heat that up and you get steam, and then you heat up the magnesium, a reaction does take place. and we get magnesium hydroxide and hydrogen. Magnesium hydroxide again is used as an antacid and a laxative. You might know milk of magnesia. If you've got a sore tummy, then sometimes milk of magnesia does the job, and in many industrial processes as well. Magnesium reacts with chlorine gas when it's heated strongly, and magnesium chloride has many industrial uses. It's used as a de-icer and a dehumidifier. So you can buy like a chemical dehumidifier. You take the lid off and it absorbs water from the atmosphere. And magnesium chloride as a supplement. We actually need a little bit of, it's a trace element in our diets. So if you're short on magnesium, taking that, I think it helps depression, apparently, if there's a shortage of it. Anyway, there's the equation. It shouldn't take long to figure out balancing that equation, should it? Aluminium, yeah, not aluminum. Aluminium is a low density metal. What we do is we alloy it with small amounts of other metals, for example, just a little bit of copper. And what you get is a very light, very strong metal, which has lots of uses. You know, aluminium cans, aeroplanes, okay, very useful. Your window frames in your conservatory, they're often aluminium. Now, aluminium reacts readily with oxygen in the air, and we get a dull protective layer. When you see aluminium, it looks quite dull, but that's on the outside is aluminium oxide. It's a bit like does the same job as paint. So it stops the aluminium underneath reacting. Powdered aluminium will burn in oxygen and you get a brilliant white flame. There's the equation there. Aluminium oxide is a white powder. In its natural form as alumina, it has a very high strength and wear resistance. It's used as an abrasive material on things like sandpaper. Yes, high strength and wear resistance. Aluminium doesn't react readily with water because of this protective layer that we were talking about. What you can do is you react it with a chemical which removes the protective layer, and then the aluminium will react with the water. Okay, and there's an equation which would be a pig of an equation to balance, I think. In the reaction, you may actually also get aluminium oxide produced. Aluminium hydroxide can be used as an antacid and in cosmetic products. Okay, it's supposedly good for your skin. Aluminium foil will burn vigorously in chlorine gas if you heat it up strongly. So there's some aluminium foil, get it really, really hot, put it in the chlorine, and yes, reaction. There's the equation. Aluminium chloride is used in antiperspirants and as an industrial catalyst. It's also used as a coagulant. It brings things together, causes them to coagulate, and it's used in water treatment. It makes all the little bits of poo and stuff stick together, and that's easier for whatever to happen. I don't know. It's used as a coagulant in water treatment. Now, I've included this table. We need to know for the oxides a little bit about the melting point. Now, basically, the oxides have all got very high melting points, and they're all good insulators. They're all good insulators when it's a solid, because there are no free electrons, there are no delocalized electrons. If they were molten, if you melt it, then they do start conducting electricity because the ions are free to move. But in the solid state, very, very good insulators. And that's the same with the chlorides as well. Yeah, in the solid state, very good insulators. You see that the chlorides still have quite high melting points, apart from the aluminium chloride. That's interesting. When you get above about 180 degrees, it changes structure, and it changes to molecules of Al2Cl6. And these molecules, the forces between the molecules are weak, and so the melting point is low. Okay, remember that little note about aluminium chloride. And then the last thing I'm going to say on this video is we know all about period 3, so sodium, magnesium and aluminium. Now metals, well, all elements are in the same group, and they're put in the same group because they have similar properties. So that means that sodium, magnesium and aluminium, and then if we looked at potassium, calcium and gallium, we would predict that they would behave in a very similar way. So lithium would be very similar to sodium, sodium would be very similar to potassium, and the compounds that you get would have similar properties as well. So lithium chloride and sodium chloride and potassium chloride would be very, very similar. One difference with the elements is reactivity. So as we go lithium, sodium, potassium, rubidium, cesium, is it francium, it gets more and more reactive. And then going at the top, looking at the period, it gets less reactive as we go from right to left. So there are some differences in reactivity, but in terms of the actual reactions and the compounds that we get, there are a lot of similarities. And with that in mind, we can make predictions.